Thank you, Chris, for the kind introduction. Hello and welcome everyone to my talk. So today I'll be talking about the roadmap towards autonomous open-end learning. As Chris introduced, I'm a PhD candidate at RIT in my final year. So this is going to be my outline for today. I'm going to briefly motivate the problem. Why and where does open world learning appear in our daily lives? Briefly define the problems, talk about some of the common elements that any open world learning system requires, which will be around continual learning, class discovery, and robustness against out of context scenarios. I'll also talk about some of the current works and some of the works that have been already published and also works that are still in progress. Finally, I'll summarize our contributions on these topics and then suggest some open problems that are still existing in the field and then open up the floor for Q&A and discussions. Okay. So I want to start with this picture of a classical machine learning pipeline. Let's talk about an offline supervised machine learning setup, right? So what usually happens is you collect a lot of labeled data, create train, val, and test splits, train your model, and then finally evaluate the model. This is what a typical life cycle of any supervised machine learning setup looks like. There are common assumptions that run through any such supervised setup, and these are train and test splits or data sets are IID, and the data distribution remains fixed over its lifetime. Now, this is a closed set assumption. And this might be okay for many narrow AI tasks. For example, if you are doing something very simple such as disease classification, and maybe you might get away by just training your model on MNIST dataset. Or let's say you are doing some product recommendation systems, then just working with a very closed set of dataset might be enough, right? But the goal with AI, at least in past few years, is we want to take these models and deploy this in the real world, right? But in real world, what we need is not just working working great for just one single task, right? We want it to generalize well on multiple tasks. So in a sense, we're moving from narrow AI towards more general AI. So but the problem in real world is it's really dynamic and it's always changing in a sense that the data set distribution can change over time. And the real world environment can also provide noisy data, out of domain data, or sometimes even novel data. So the model needs to deal with all of these scenarios, right? Another data-specific problems for supervised setups is that it's impossible to collect data from all different scenarios that I mentioned above, right? It's really impossible to have all different types of data. And the next big thing is that it also requires a lot of annotations, which really requires a lot of effort. So I talked about the classical closed world assumptions, but what are the risks associated with just deploying this closed world models and then deploying it out in the real world, right? So we have heard about many of these incidents happening recently, Tesla crashes where it can't recognize some objects in the roads, or AI algorithms being branded as racist, biased, and discriminating against minority categories. This has been a real problem with just taking these closed world models and then deploying it in real world. And sometimes this could prove fatal, where people have found that Tesla had accidents in those cases. So especially if we are talking about applying AI in healthcare, we need to be even more careful about just deploying these sort of models. So what we really need is an adaptive learner. So just like humans, what we need are in real world is that models that can adapt to change quickly, right? So the one main thing that I want to focus on today is that we need to move away from this paradigm of fixed train and test stages, right? For example, let's look at human learning. What happens if you have a human in real world? What usually happens is that if you see a new instance X, you apply your knowledge that you have learned until time step T, and then you immediately test on that instance, right? So whatever the results for that test might be, you might get the instance correct or you might get it wrong. But immediately after that time step, it becomes your training data, right? So there is not a fixed train and test, but instead it's like a never-ending process where the agent is always learning. And so this points towards online continual learning, where the learning never stops and it keeps on going on forever. So that's one main thing that I want to point towards, where um, it's clear that learning from a fixed data set is not enough in real world, right? And one can easily come and say, hey, you can gather more data, but gathering level data is always expensive in terms of both time and money. And one good solutions, nice solutions, workaround solution for that is using self-supervised models. Past few years, self-supervised models have been up to the par of supervised models, and that would be a good direction to move towards. So here, for this purpose, an ideal system would be an online continual self-supervised learner, right? So there's some elements of never-ending learning and also deriving supervision from within the data by itself. So we are not using human annotators where we're in the system labeling the data all the time. I would also like to point out that this is still an ideal version of the system. We are nowhere close to it, but then I'm going to propose some few words that will take us close towards this idealized version. We have, especially I'm going to talk about two works that's more scalable, meaning it can work even in the large data set regime. And also we have found that they are more efficient compared to previously made models. Okay, so let's define the difference between open set and closed set assumptions, right? So if you see here, this is a three-way classifier. You have three object categories. Now in a closed setting, what you are doing is partitioning the decision or the space into three partitions, right? And the assumption really here is that all the space is equally partitioned between three categories. Now, what that leads is to unbounded decision boundaries. With what meaning, if there is any unknown, it is forced to be mapped into any of these three partitions. Right? So that's the closed set assumption. And compared to closed set, in open set, it is assumed that unknowns will exist, but then instead of partitioning the space, you are creating sort of sets, and along with that, unknowns will also exist. And you are sort of changing the K classifier into K+1 classifier based on this acceptance function as X, which will allow the model to say that K+1 class is an unknown category, and it will reject those unknown examples. So that's open set, right? So the difference here with between open set and open world is that in open world, we just don't reject the unknowns, but after we detect these are the unknowns, we also try and have the model learn those unknowns as well. Okay. So how do you build an unknown aware model, right? So this is your closed set assumption, and we want to move into a open set um, assumption here. So you can see this is a four-way classifier, and this now becomes a five-way classifier where you are rejecting the unknowns, right? Which are the samples which are far away from any of the classes that has been known to the classifier. So if you're taking a multi-class classifier, your classification models produces logits. So classifier model is fx, which produces logits for class 1 to k, and you define an acceptance function for each of the examples. Now, based on a threshold delta, what you are saying is, if I know that this sample is similar to what I've seen before, you want to classify it into one of the k categories. And if it is below some threshold, you want to say it's the k plus 1 class, meaning it's an unknown class. So that's how generally we build an unknown aware model. So compared to this, now how does this come and fit into an open world setup, right? So in open world, it's assumed that at time step t, you have knowledge of some categories. Let's say you know about apple and mug, but you don't know about bananas, right? And after some learning, you are quite confident that it has learned about bananas. You go ahead and incrementally update your model, meaning at knowledge at time step t plus 1, your knowledge now updates, has also the knowledge about the banana categories, right? So the goal here would be to incrementally add the unknown classes after the model is confident towards some degree. It will be added to your known categories, and it keeps them going until you have no any unknowns left. So that's how a typical open world learning problem is set up. I'm going to talk about two open world learning flavors here, in this talk today. The first one is talking about known class with novel attributes. And this I refer to as out of context scenarios, right? For example, usually you see cows near, it's grazing, surrounded by grasses, but what happens if cow comes into a very novel situation or something like near an ocean, right? Or let's say you're seeing normal cars, but then you all of a sudden see a rainbow colored car. So either the environment is novel or the object is novel because of a novel attribute itself. So that's a known class with novel attributes. And what we are hoping here is to build robust models that are robust to unknown attributes associated with the object or the environment. The second flavor here is awareness of novel class data, meaning I see a category that I have not seen during my training, right? For example, if it is an ImageNet trained model, all of a sudden, if I see a dinosaur on the street, what should the model do, right? So the goal with this is to detect and learn from the unknowns as well, right? But before moving on to this, I want to highlight some progress on in online continual learning that will be necessary for any open world systems, right? So we need to learn in a continual manner. So I want to talk about our paper Rodeo, which is published in VMBC 2020, where we created the first online streaming learning systems specifically tuned for object detection. So the motivation here is that the best object detection methods, they can perform update as soon as new data is available. That means they can't learn incrementally. So there is a huge waiting period the model just needs to wait before a significant amount of data is collected, and then only it can update the model. So that's a very limiting feature, right? And so this makes the model not suitable for dynamic scenarios where data is constantly evolving and changing over time. And this could happen because of just season changing, or backgrounds change, new object categories appearing over time, talking about internet trends, they always change. And so various reasons for this change, right? But today's artificial agents needs the ability to overcome these limitations and really incorporate those changes during their training. For example, robotics or edge devices or AI agents, we want these agents to change over time. As you are growing, we want an AI agent to change along with you. Right? So that's the real motivation behind the online streaming paradigm. So beyond the benchmark tests, we applied this model, and we won a second place position in a ICCV 2021 challenge that was recently held, where the goal was to perform continual 2D object detection for domain changing environments, right? For example, let's say if we are taking a self-driving car out in the street, then weather could change, or the period of when you're driving. If you are training your system during daytime, what happens if all of a sudden you drive during night? How do you handle such changes, right? That was the goal behind this challenge. So before moving on to our online model, let's talk about the offline model that is usually followed, right? So in offline, what usually happens is in a single time step T, you see all the categories, right? And you have some system that produces the reason proposals, which are the object candidates in the image. You pass it through an object detector, and model predicts the bounding boxes and object categories, right? Yet all of these happens in a single time step T, where model sees the examples for all categories. Whereas in online streaming learning, the model receives instances incrementally one at a time and only gets to perform a single pass throughout the entire data set, right? So we are not seeing the data set multiple times, right? For example, consider this streaming learning setup where for different time step T plus 1 and T plus 2, you have 3 different categories appearing one after another, right? And so this is an extreme case. However, trying to model and learn from this situation makes the learning even closer to how human beings learn, right? So we do not loop through some data set for multiple times. And this is also suitable for having real-time applications where immediate learning is necessary. However, the challenge with this, since the data is non-IID, is catastrophic forgetting, right? Now, catastrophic forgetting refers to a phenomenon where you sort of forget previous knowledge when you are learning new information, right? And so one solution to mitigate forgetting, one very efficient solution is replay, where you store previous examples in a buffer, and then if you want, and when you're learning, you mix new instances with the old ones and fine tune the model. So this is a very efficient approach but one caveat with just naive replay is, which considers storing just raw pixels, right? But this is not biologically plausible, and it's also not clearly defined for object detection. So in contrast to using just such naive replay, in rodeo, our approach is to use quantized representations, which are much more memory efficient to store. And moreover, we also specify a memory budget that the model can exceed, right? So it's trying to simulate a real world system where resources are constrained. So just like in a real rodeo sport, we want our models to be able to detect and learn new changes immediately. So there are 2 key components that I wanted to mention quickly. The first key component is that allows for streaming update is controlling the stability plasticity by freezing parts of the model, right? So this is also motivated by human learning, where we only update higher or task-specific learning areas, right? The second key idea is storing compressed representation from intermediate layers for replay using tensor quantization. This is also motivated by the hippocampal indexing theory, where we store the indices of quantized representation and then later retrieve those representation using the store indices. Okay, so let's compare a typical offline model to our rodeo. So you can see the component number one, where we split a fast RCNN model into a fixed split of the model Z and a trainable person F. Right? So that was the first component. The second component here is the replay component, which is stores the quantized representation and reconstructs it during replay, and then updates the trainable portion of the model. Right. So briefly talking about product quantization, what it is doing is it's an effective vector quantization method. And so if you know about k-means, which compared to k-means, product quantization decomposes the higher dimensional space into the smaller subspaces, and then quantizes these subspaces separately, right? So this allows it to generate like very large code books at very low memory and time cost, right? So eventually, if you want to store this matrix V cross E, users can use the indices and your trained PQ model. You can just represent this matrix using these indices. So that's the idea behind the product quantization. So with all these elements, I want to compare model with compared to offline model and some other previous models as well. So first, this is for a large-scale object detection data set called COCO, where rodeo achieves a set of odd results. And as you can see, fine-tuning, just simple fine-tuning does not mitigate forgetting. Similar results for VOC dataset as well, where we even beat a previous state of art incremental BATS model that uses distillation. So our streaming model is better than even BATS detection models. So the outcomes were really the streaming learning models allow us to learn from evolving or changing data. And in rodeo, we pioneer a novel streaming object detection model that uses tensor quantization to store hidden representations during replay. We established strong baselines for two large-scale object detection dataset. And not only that, our model is very efficient. We are 40 times faster compared to an offline model on the COCO dataset. But rodeo is still not going to take us to an open world learning system, right? We address some of the challenges in open world learning, such as continual learning, but our system needs the ability to identify knowledge gap in itself, right? So this is pointing towards object discovery, where we need to assign unseen classes to their own clusters, right? So that's the goal. But before moving towards object discovery, I want to tackle another problem that I discussed previously, which is regarding out of context objects, right? So here again, talking, the goal is to make robust models which are robust against unknown attributes that is associated with the object or the environment. Okay. So this was the work that was done during my summer intensive at SRI International, and this is still under review at Isaac High 2022. So here I saw a chart where different quadrants show here that in the first quadrant here you can see that most of the ML frameworks that is trained for object detection operate in this regime, where we have known objects in known context, meaning cows are usually seen grazing around grasses, or cars. We don't see cars flying, but usually on the road. So these are like your normal scenarios, right? So standard machine learning frameworks usually operate in such dataset regimes. So datasets such as COCO or VOC fall into this category. We will also talk about open set and open world learning, where we are dealing with unknown objects. But for this work, we are trying to tackle known objects in unknown context, right? So you have seen, for example, you have seen elephant in your training time, but then all of a sudden now you see elephant in your kitchen, right? So how do you handle or detect such scenarios? So for that, what we found was just naively using object detector output cannot model the relationship between objects and the context, right? So if your typical object detectors will just produce bounding boxes, but there is no any concept of relationship between these bounding boxes in the scenes, right? So our approach here is to, once we get the initial low-level predictions, for example, your bounding boxes, the category levels, and the coordinates, what you can do is have or try to get some higher level contextual cues derived using graph representation of objects, right? So here we create a graph of all the object categories found, where each node is the object category, and there exists some edges between these nodes, right? And the goal is to say that these categories are in context, and within given this scene, elephant is an out of context object. So we propose a graph contextual reasoning network where the input is an image graph, G with vertices V and edges E. And so this flows into two components here, the representation graph and the context graph, right? The goal of the representation graph is to learn object-dependent representation, right? So you want to learn object-dependent representation so that you can separate between one object from another. The second graph here is the context graphs that learns the contextual dependency of objects, right? So it's really saying that, hey, is this elephant relevant to this context or not, right? So, and at the end, what the model does is, for example, for a person, it will check whether the person matches to this context. If it matches, then it's an in context object. If it does not, for example, for this elephant, it's an out of context object category, right? So both of these graphs are realized by one of the most popular graph frameworks called using graph convolution networks. I would also like to point to our archive paper for more details. But briefly, I'm going to talk about context dependency as well. Context dependency is really simple, where it takes in object labels and other attributes as well, such as size and position in the image, and learns the contextual dependency. In our work, we take size and the position of the objects in the image as additional features, but then this is limited by the image domain we have. For example, if we have like 3D images, you could also incorporate other information such as depth information for even greater accuracy. I would like to point out that this task out of context prediction is much more harder than one of the tasks that is usually discussed called out of distribution detection, right? So in out of distribution detection, for example, the task is for this, the picture here is an example for city sketch images, which is usually a road scene data set, and you pick out object categories from other data sets such as VOC, and you just paste it into on top of these images, right? So for this, VOC are out of distribution object categories. And so here I would like to point out one of the results from the paper by Bloom et al. From the physics paper. What they found was even softmax baseline is really competitive to some of these state-of-art and state-of-art approaches, which are really complicated methods, right? So even simple softmax baseline is working well. So before showing some results on some existing data sets, I want to introduce our data set that we specifically made for out of context detection, where we have 100K images generated using the COCO data set, meaning the in context objects and out of context objects both fall within the COCO data sets. The out of context objects, they usually violate the co-occurrence and size priors, right? So it's not really ideal that the airplane is within a kitchen, right? So all of these bounding boxes refer to out of context objects. So I talked about softmax confidence for out of context, out of distribution detection, right? So it was really working well there. But for us, comparing with other baselines here, you can see softmax base confidence is really working really poor when we're seeing the AUC metrics. Compared to that, GCRM is working very well, 0.98. And you can see the importance of modeling the context here, right? So if we do not have the context dependency model, you only get 0.58. So that really shows the importance of modeling the context. We also have other studies showing the importance of having different kind of bounding boxes and different sort of accuracy of levels associated with those bounding boxes. So you can see if you use Oracle boxes and levels, the performance is really high. If you use Oracle boxes, but then predict the levels from our representation learner, then the accuracy goes a little bit below. And if you're using predicted boxes and predicted levels, which comes from, like, let's say, mass RCNN or some other box proposal methods, then the performance is even lower. So what that means is that if you have better bounding box features and labels provided, the systems, our system can get even more better. One of the main feature of our model is that our model is very tiny. And it is only about 9 megabytes, right? And the training takes only 2 to 3 hours on a standard GPU. The inference is roughly only 0.25 seconds. So this is a very efficient model in detecting out of context scenarios. Another interesting finding that I want to point out is we were looking to find the answer for just investigating that if the modern detectors are using leak context, and it turns out they are, right? So the implication of this is that this can lead to biased models, right? So it's a bias is a huge problem in the AI community, where especially you can find that models are discriminating against the minority categories, and this can also lead to shallow and brittle representations. Right? So this is not the main finding of our paper, but I'll be happy to talk about this if somebody wants to talk offline. So I want to move on to the next open world learning flavor here, where we want to detect novel class categories, right? So briefly recapping open world learning features, where we want to have incrementally update the model of the known categories as the new data arrives. We also want to detect whether the incoming data is known or something that needs to be learned, right? If it is a known versus an unknown data. And we need to learn new categories not initially seen during training. And this also happened without retraining everything from scratch as compared to any offline models. So we're talking about class discovery here, right? So what do I mean by class discovery, and like how is the overall framework set up? So here you can see the input, which consists of images, several images where you have both labeled and unlabeled shown here in dotted categories, right? The goal is to create a model that can discover new objects, right? So here horse is unlabeled, right? So you want to discover that horse is a new category, but also not forget about whatever it has learned previously, classes A and B. So again, this is an ongoing work. Some of the components we are still trying to figure out, but I just wanted to give a high level overview of our pipeline here. So we want to have some of these components here, such as self-supervised learning and a universal proposal generator. So what does this mean, right? What does these models allow us to do is, if we have self-supervised model, it helps to learn representations without needing any external labels. So remember, in an open world learning, it's infeasible to label every time, right? So we want to have model that can learn from the data itself rather than constantly being provided the feedback externally. Right? So that's the goal of self-supervised learning. Proposal generator, if you're talking about object detection systems, we want to generate candidates which represent that objects appear in, candidates really say that these portion of image have a high chance of having objects in them, right? And after this, the next component we want to have is an unknown known versus unknown detector. And after the unknowns are detected, what we want to do is we need to cluster similar categories together and also update the model with this new knowledge, right? So clustering and pseudo labeling is the next big important portion of this model. Recently, there has been some nice progress in the field of unknown discovery. So one particular exciting line of work is energy-based models, where if you feed an example X to your CNN model and given an energy function, it will produce a distribution of a score, which is really bimodal, meaning you can easily separate between out of distribution versus in distribution examples, where based on some threshold, you can easily separate between knowns and your unknowns. So unknowns would be your out of distribution examples here. It has also been shown to be very effective compared to softmax scores. And if you want to read more about this, this is a paper by Liu et al. Published in Neuros 2020. However, a word of warning before using this method, one needs to think about data quality and size, etc. So this was one paper that came out in CVPR 2020 where they are just evaluating on CFAR datasets, right? So in this, it's clear that Mulholland-based method is winning ODIN-based method. So both of these are out of distribution detection methods, and Mulholland-based is clearly winning ODIN on many of these data sets here, right? But once you move this from the smaller data set regime and move into larger data sets such as ImageNet, the rank is completely flipped here, right? So you can see ODIN is better, much better than Mulholland-based when you're talking about ImageNet. So we need to think not just about the method, but also about the data quality and size, and many other factors needs to be considered before just transporting this model to other domains. The next big thing that I want to talk about, which will be very important for open world learning system, is clustering and pseudo labeling. So once we have the unknowns and even knowns, we want to cluster them in a single space where if a new example comes in, we want to assign it to any of these clusters, right? So what are the good ways? What are the good ways to do it? One simple approach proposed by Yang et al. Is to use this agglomerative clustering loss, where based on a function of distance between these two clusters, you assign the sample into one of these clusters, right? However, there are still open questions for this. For example, how do you operate when the number of clusters are not given a priority, right? So you have no idea of how many clusters should be formed in that data set when you're learning incrementally. The next question is, what sort of semantic categorization should we enforce on any clusters, right? Or should we let them emerge organically? What I mean by that is that all of these images refer to chairs, right? Functionally, they can serve the purpose of being a chair, but visually they are not similar. And since our model is operating in a visual world, how do you enforce such semantic categorization? Is also going to be a very interesting question that we might need to explore. So to finally summarize, deploying closed world models without realizing open world risk can have severe real world consequences. We have seen a lot of examples during recent times about this. To adapt to changing world, we need a continual learner, right? And in Rodeo, we develop a continual object detection system that can recognize new objects over time. Addressing the open world, which changes rapidly, also needs a system that can learn the context, just like our graph contextual reasoning network. Um, Next, current supervised models cannot handle novel categories, right? These, which can be readily encountered when we are deploying models in real world. So we need models that can perform open world learning with also capacity to discover new object categories. Right? I also want to put out a bonus question here. Until now, we are just focusing on a unimodal system, right? But humans and other mammals just don't learn from just one modalities. How do we build? The question would be, how do you build open world multimodal learners? Finally, I would like to thank you all for coming to my talk. These are the links to the papers that that went into this talk, and I would be happy to answer any of your questions now. Thank you.